Great. Okay. Yes. So thank you to the organizers for arranging this wonderful workshop here, and thanks for the invitation to speak. So I want to talk about some work I've done here with Çağlar Uyanık. Really, the goal here of the project that we're working on here is to try to look at free group extensions. So really, the types of free groups extensions we're looking at, arise from looking at the short exact sequence that relates the outer morphism group to the outer automorphism group. Right, so if you're given a subgroup of the free group, you can take the full pre-image in the automorphism group, and you get an extension of the free group F. So P here, sorry, P inverse of H is the extension group, just looking at the full pre-image. And so really the goal of what we're looking at is trying to come up with some robust conditions for showing that the group, the extension group EH is a hyperbolic group. Okay. And so when you're just thinking about any extension of the free group, really hyperbolicity really comes down to understanding extensions that arise in this way. Just ones that arise by looking at subgroups of outer automorphism of the free group. Okay, so question? Okay, and of course, there's a long history to this question, right? Dating back to Thurston's work on free manifolds that fiber over the circle. That tells us exactly when, not thinking about a free group, but thinking about the fundamental group of a surface, tells us when the extension there, when the group Z is infinite cyclic, tells us when the extension there is going to be hyperbolic. And then, of course, there's work of Farb and Mosier and Hammerstadt about coming up with a notion of a convex co-compact subgroup of the mapping class group, which is exactly when the extension group is going to be hyperbolic, and further work on Kent and Leininger, also sort of relating that dynamically to some other objects that'll arise here. But let me mention some of the results here that are known for free groups on this question. So the first one here I want to mention is due to Brinkman. Brinkman gives a characterization for when the extension group is hyperbolic in the case that H is infinite cyclic. Obviously generated by some outer automorphism phi, is isomorphic to Z. So an infinite order element. So I mean, he proves really that, if you think about the only obstruction to hyperbolicity, right? So if you have some element, which when you think about the outer automorphism acting on the free group, if you have some sort of periodic conjugacy class, that's going to close up in your group to give you a torus. And so that's definitely going to be an obstruction to hyperbolicity. And Brinkman proves that as long as your outer automorphism, doesn't do that, as long as there are no periodic conjugacy classes, then in fact you get hyperbolic. The extension will be hyperbolic. Right? Okay. Then the next one here I want to mention is due to Spencer Dowdle and Sam Taylor. Okay, and so they come up with a sufficient condition here for saying when the extension group is hyperbolic in terms of the action of H on some complex. So they prove that if the orbit map from H into this Z factor graph here that I'll explain in a moment is a quasi-isometric embedding, the extension group is hyperbolic. So if you're familiar with some of the story from surface group extensions and the theory with convex co-compact subgroups, this looks very similar to the story that's going on there, right? So one equivalent characterization of a convex co-compact subgroup is that the orbit map from the subgroup of the mapping class group to the curve complex is a QI embedding. And in that case, that's exactly giving you a characterization of when that extension group is hyperbolic. Okay. And so what Spencer and Sam showed, right, is that if you have this orbit map and it's a QI embedding to this complex, then you necessarily get an extension group here that's hyperbolic. But it's known that this is not a characterization.
H is what that you started with. Who is H?
Oh, H. Oh, sorry. I'm just starting with, sorry, this should be like an injection. Sorry. I'm thinking of a subgroup of out of 10. Okay. Yeah. So it's not a characterization in this case. So, I mean, even in the case when H is infinite cyclic, this is not a characterization. So there are these elements that are H-toroidal that don't have any periodic conjugacy classes, but really their orbit map to the Z factor complex is not going to be a QI embed. Okay. really, it's these elements here that are really sort of, mixing up the free group just on the level of conjugacy classes, but there's some free factors there that are getting preserved. And so we're interested here in, like I said, getting some more, like robust conditions here for coming up with when the extension group is hyperbolic. And so really what we need to do is we need to keep track of some of this relative data. We need to keep track of the free factors of the free group and how they're getting mixed up with the subgroup. Really, I want to be working with the free group, but thought of as a free product. I want to consider F, what's a free product decomposition. So write it with some, as a free product of some subgroups. And then, some free group that's also left over. Okay. So I want to think of the free group as a free product, because I really need to keep track of what's going on with these free factors in order to try to get a condition that's going to be more robust for showing that certain extensions are hyperbolic. Okay. So yeah, just some notation here. I'll denote the collection of conjugacy classes of these free factors just with the fancy A. All right, and really, a lot of what we're doing works in a more general context as well than just free groups. Really, we'll just be talking really about more generally just about free products, where you can really replace these A's with essentially any group that you want to. We really use a lot of the machinery that Chris was talking about the other day. I want to think about this as a relatively hyperbolic group. And so really the AIs, I mean, I'll always think about these as being free groups, but you're free to put in, essentially your favorite groups there if you want to. And, the results I'm going to claim later on are still gonna hold. Okay. I do need to work with torsion free. I need torsion free at some point. So as long as everything here is torsion free, the torsion free product will be just as fine. What?
All the groups are free groups.
Yeah. Oh, no. So I mean, because I want to like keep track of like these ones here. Those ones. Could be whatever. Yeah. I mean, it's yeah, I mean, you can think, you have some graphic groups decomposition for the free group, right? And so with, like triple edge stabilizers. So we're just keeping track of like the vertex group. Okay. So yeah, so I want to look at a couple spaces of trees here related to the free group and this free factor system. And look at a map between them. So let me just start off with the definition here of an FA tree. So this will just be a simplicial tree with a co-compact minimal action of F, where each of the AIs has a unique fixed point. Okay. So I mean that's what's special about them. I'm keeping track here of these trees where each of these free factors has a unique. No. Okay. So there's two spaces of trees here, like I said, that I'm talking about. The first of which is this relative outer space that Riley was talking about the other day. So I just want to think about this as a set. This is a topological space. Riley was talking about the topology on it the other day. But really, from the point of view of the talk here, I'm really just going to be thinking about this as a set. So as a set, this is really just metric. Let me start off with the other adjective. So relatively free, metric FA trees. So relatively free just means that the only elliptic elements are the peripherals, right? So these things need all of, like these peripheral subgroups or those fixed free factors need to have a fixed point. And I'm just saying everything else acts, hyperbolically. Okay, and like I said, there's a natural topology on this space, as Riley was talking about the other day, but really I'll just be thinking about it as a set. But you can think about, like points in this space, as like graphic groups decompositions of the free group. Okay, so you have some sort of graphic groups decomposition here. Maybe some of your vertices have some non-trivial stabilizer. All the other ones there are going to have this trivial stabilizer. Okay, as Riley was saying, right, you sort of vary the lengths of the edges and you can kind of move around. Okay, the other space that I want to talk about then is this thing called the Z factor graph. Okay, so this is also, related to these trees, right? It's built out of trees. So the vertices of this graph, I'll call this ZF. So the vertices are going to be FA trees where the edge stabilizers are either infinite cyclic and peripheral or trivial. The edge stabilizers are cyclic and non-peripheral, right? So they're not conjugate into one of the AIs, or they're trivial. Okay, so those are the vertices of the graph. Oh, no, I think still cyclic. Okay, so those are the vertices. And the edges. So the edges, let's see, so there's an edge between two of these trees, T1 and T2. If the trees are compatible, I'll say what that means in a second here. So compatible. Yeah, so I mean, you should think that this complex is really, one of the analogs of the curve complex for a free group. And so this notion of compatible is really just, generalizing the notion of what it means for curves to be disjoint. That's how you should think about this notion here of compatible. So what does it mean to say that they're compatible? And so two trees are compatible if there's another tree that collapses to both of those, right? So these maps here, I'm just, collapsing some edges. Okay, like a good example to think about is, maybe the 3T naught, is going to be something with two edges corresponding, to some sort of a amalgamation here of these three groups, A, C, and B, right along these subgroups. And if you just, collapse one of these edges, say I collapse that edge over there, and I get something that looks like, the free group of amalgamation A over A with group B prime. Or I could, collapse the other one, call that subgroup A prime. And I'll get a different, tree, a different graph of groups decomposition. That's what it means to be compatible, right? You have some like larger tree or some larger graph of groups decomposition, and you're just collapsing, some edges to get from one to the other. And this really is, like the picture of disjointness in a surface, right? If you have a surface, your simple closed curve corresponds to a splitting by Z, right? And if those curves are disjoint, right, then you can realize those together in a single graph of groups decomposition. Okay, so one edge here is this notion of being compatible, which, like I said, you should really just think about as, saying that the corresponding to disjoint things like disjoint curves. And then we also add an edge if there's an element that's elliptic in both, or there exists, a non-peripheral element. So if I just add these edges corresponding to the trees being compatible, we get this graph, which is called the Z splitting graph. And so we're just, doing an electrification there, just adding a whole bunch more edges corresponding when two of them have a common, non-peripheral elliptic element. Okay, well, yes, do you have a question?
I read non-peripheral correctly.
Okay. Okay, so I mean, there's a natural map from the relative outer space to the Z factor graph, right? I mean, one of these relatively free trees is in fact, I didn't give a name of these. These are what are called Z splittings. So one of those points in the outer space, right? That's a relatively free tree, and that's the Z splitting, right? Because I'm allowed to have trivial edge stabilizers. So really, there's a natural map from the outer space to the Z factor graph where you just forget the metric. So this map from pi from outer space to the Z factor, which is just, forget the metric. Okay, and so I can almost state the main theorem here. It's really about this map here about showing that something over there in that complex, the Z factor complex, is bounded. So just one more definition here, notion of a combinatorial length. So the combinatorial length of some element is just count the number of edges in a fundamental domain, right? Or look at the axis of the tree. Right, take the axis of the element as long as it's hyperbolic and look at how many edges there are in the quotient. Oh, number of edges here. Okay. And if it's elliptic, just say that's 0. Okay. So I have this notion of a combinatorial length there for one of these trees, just counting how many edges are in its axis. And so then the main theorem here, in words says, if I look at like the portion of the relative outer space where a given element is short, then that has bounded diameter in the Z factor complex, where the diameter bound just depends on the length bound. So for all L, there is a D, such that if G is non-peripheral, then if I look at the subset of the outer space, where the combinatorial length of my element is at most L. Okay. I can take the projection of this, or just think about this as, like a subset of the Z factor graph, just by forgetting the metric, and the diameter of this subset. All right, so let me give a couple of remarks here on this. Well, I'm going to call this subset here O sub L of G, right? The region where G has length at most L. Okay, so yeah, I guess the first thing is you might ask, what does this have to do with like the first 5 minutes of my talk where I was talking about hyperbolicity? Okay, well, so I mean, like I said, we're trying to get this more robust condition, right? So we're trying to, really need to look at not just, like a single Z factor graph, but really like this family of Z factor graphs, okay? And what does a condition like this tell you, which is useful for proving something like hyperbolicity, right? It's saying that, like, if I'm moving in the subgroup and I'm making some definite progress inside of the Z factor graph, then elements aren't staying short for too long, right? That region where I'm like moving through, right, only has some sort of bounded diameter in the Z factor complex. So I'm actually making definite progress. No element is staying short for too long. And it's these types of statements then that you want to like convert them into some sort of, uniform type flaring. All right, so we're still, we're making some progress on that latter step. But, as we were going through, this was a key part here of the proof that in the absolute setting, for some reasons I'll hint out here in a little bit, is a little bit more difficult than in the absolute setting where you just think about just dealing with free groups. There's something really different here about the relative setting where we had to work a little harder. Okay, so that's how this is related to hyperbolicity. Okay, but I also want to just translate this statement for you in the context of surfaces, right? If you just sort of think about what is this statement, if you were going to translate everything to surfaces, right? Well, like I said, the Z factor graph really corresponds to the curve complex. The relative outer space is going to be the Teichmuller space, space of hyperbolic structures on your surface. And then this projection map, I claim, is really just a syscale map from Teichmuller space to the curve complex, where the syscale of your point in Teichmuller space is just, the short, let me just say is in quotation mark, the shortest curve on X. Right. I mean, there might be two of them, but, that subset inside of the curve complex has bounded diameter. So, this is sort of coarsely well-defined. Okay, and if you just, stick those words into the theorem, I mean, you get this, I guess I'll call it a folklore theorem. That if you look at the region of Teichmuller space where your favorite curve has some bounded length, then, the collection of syscales there is going to be some bounded diameter subset of the curve complex. That's that, for all curves, gamma in your surface, you can look at the, region of Teichmuller space where your curve has, length at most L. You can look at the collection of syscales, and then you can look at the diameter. Then that's going to be bounded by P. Okay. So like I said, I mean, this, when we, first kind of wrote down this theorem, we were thinking a little bit about the case for surfaces. And I asked around if anyone like had an actual written down reference for this theorem. I asked like Jing, I asked Chris Leininger, I asked Yair. No one had knew of any spot this was written down, but they all knew about this theorem. So I'll just call it a folklore theorem here. But for the rest of the talk, then I really want to give like a proof, or sketch out some of the details here that goes into the proof. And in fact, both of these you can really kind of prove in a similar way. There's really some sort of parallel structure in the way these are done. So I kind of want to sketch out a proof for the surfaces one at the same time I sketch out the proof for the free group one. Yeah, that's a good question. Yeah, so you might ask, why am I not using the metric length? So like the proof here that we use like really uses the combinatorial length. And like what we need it for is going to use the combinatorial length. I mean, so I think we can also show that it's true for the metric length as well too. So we don't have all that details for that one written down. Okay. Yeah, so the proofs of these, there's sort of three cases that you want to consider. And just for simplicity, I'm going to stick to like the absolute case for the free group case. I'll sort of mention where you need to like make some additional assumptions, or where you need to do some additional work for the the relative case, and sort of why that case gets a little harder at times. So, we'll just assume that A is just empty. Right? So we're really just dealing with, free groups, and then this is outer space. Okay, so the first case, to consider is if you have a simple curve, right? And this is, really, probably some of the first things when you start thinking about the curve complex, about trying to get some of these distance bounds that you come across is really the argument here, right? So, I mean, the thing is, if, X, is in this region, oh, sorry, same thing. I'm just going to denote this by tight sub L of G, the region where G has length at most L. Right? So if the length of G is at most L in X. Oh, yes, sorry, thank you. And alpha is a systole. Well, right, I mean, so the point is that, like, since alpha is a systole, it has some sort of, short length to it. And so every time gamma intersects alpha, right, it's going to have to cross this big annulus, right? And so you can bound the number of intersections between alpha and gamma by, some constant times L. And then, one of the first things you do when you start looking at the curve complex, right, you learn how you can bound the distance between the intersection number, right? Really, it's going to be less than the log of it, but it's going to be less than it. Okay, and so that does it, right? It tells you that, alpha is going to have distance at most is constant times L to the curve gamma. So gamma is really like your center point that you can kind of measure the distance to. So this tells me, that the diameter here of this subset, is going to be less than, like 2 times this constant times L. Okay. Okay, simple enough, right? Okay, so let's do it now for free groups. And so again, I'm going to look at simple elements first. And I'll suppose, G is simple. So what does simple mean here in the context of free groups? Well, you can think about it in one of two equivalent ways. One, it's contained in a proper free factor. Or another way to think about it is that it acts elliptically in some free splitting of F. Right, where free splitting is just a Z splitting where all the edge stabilizers are trivial. Okay. And so, I mean, this case is also pretty straightforward, definitely using a lot of well-known stuff. The main tool here is the notion of a Whitehead graph. So let me give you sort of a non-standard here definition of the Whitehead graph that is really useful for the stuff that comes later. So if you take, your tree in outer space, then you take some vertex of the tree. One way to talk about the Whitehead graph is the following. So it'll be the graph here where the vertices correspond to the components of the complement of that vertex. Okay. So you remove that vertex from your tree, you have some components. Those components are going to be the vertices. And when do you connect two of them up by an edge? So I connect two components, say y1 and y2, by an edge. If the axis of G, right? If some translate of the axis of G actually meets both of those components, right? So if some axis of the axis of G meets both of those components, I'm going to add an edge between them. Okay. I mean, a lot of times people talk about, the Whitehead graph, right? I mean, if you're talking about, like a basis of the free group or something, right? You have a vertex for each generator and its inverse, and you sort of look at all of these two-letter subwords. All you're really doing there is you're just recording like the turns that that element takes, right? And that's really what's going on here, right? I'm just sort of recording when this element is turning from one of these components to another. Okay. But like I said, this is a nice way here of thinking about the Whitehead graph for some stuff that comes later on. Okay, and so then there's, a few standard facts about the Whitehead graph that are probably some of the first things you learn about the Whitehead graph when you start learning about it. I mean, the first is that, if the Whitehead graph is disconnected, we can find a free splitting. So written in the language here, so if the Whitehead graph here is disconnected, then there's this free splitting where, G is elliptic, free splitting, we call it S, where, G is elliptic, has combinatorial length 0, and its distance from T, or the projection of T, is at most 1. Okay. Oh, I should say, I mean, like over here, right, we were really trying to show that everything had some sort of fixed distance to gamma, right? This was some sort of point I know that I can measure myself to. over here, there's really like a diameter 1 set where like my element G has a fixed point, right? Because I've added all of those edges whenever G has a fixed point. So I really just want to show I can get to that 1 diameter set in some finite time. That's kind of the same thing as what we did over here. Okay. And I mean, this is a, really simple idea about why this statement is true. I mean, if you have your tree and there's V, Danny left, so I'm allowed to use color now. So I look at like the axes of G. Okay. And being disconnected means it looks something like this, right? There's like a top half and a bottom half. Nothing goes from top to the bottom. And I just split this open. Right. So there's this collapse maps here, call that edge E. Right. Okay. But then I can also just collapse everything else. And that's how I get S. Okay. Right. And I've collapsed all the axes of G. So now it has a fixed point. Okay. Great. Okay. And then the second thing you learn, which was something related to what Henry was talking about the other day, is that, if the Whitehead graph has a cut vertex, then, well, there's going to be some tree T prime where the length of G in T prime is strictly less than the length in T, and their distance is 1. So there's a cut vertex. I can make a step of distance 1 and, make that element a little shorter. So the picture here is also, very clear as to what's going on. So let me try to sketch the picture here. Danny, I'm sorry, we all decided that when you left, I could use color. So I'm going to continue to use color. Right. So if there's what?
This color is good. It depends on the chalk. It's weird.
Okay.
I'll pull the next guy.
Okay. So in this case, right, so the cut vertex, right, it's something similar, right? But it's like, there's this top bit and this bottom bit, and they can connect up to this thing over here, but there's nothing between the top and the bottom besides going over there. And the point is you just pop this open. You just unfold. Right? Henry was saying he likes unfolding better than folding. Right? So I can shoot. Sorry. Okay, so you can pop this open and you can unfold. Okay. And then, so call this edge, say like E1 and E2. And notice that, since that was a cut vertex there, I didn't make any of these things longer, right? If something had to like go from the top to the bottom, then when I would have unfolded, I would have made one of those axes longer. But since I can cut this open without making anything longer, now I can like collapse the edge E2 to get this tree T prime. Okay. And in here, I know that, the length is less than the length in T. Okay. And well, these ones are compatible. There's sort of this like intermediate tree here as well too, where you sort of, only unfold halfway. So you can sort of only unfold halfway. Call this like E1, E2, right? So collapsing E1 brings me, or I don't know. Yeah. Anyway, you see, right? So collapsing different ones of those, you can see how those things really have distance 1. Okay, so don't just unfold half. Okay, well now, you use the famous theorem of Whitehead that whenever you have a simple element, you always have one of these two things. You either have a disjoint graph or you have a cut vertex. It's disconnected or has a cut vertex. Right, for some V and T. Okay. Okay, well now we can prove the statement here for simple elements. So if I take my tree, where my element G has length at most L, then by combining these, right, I can just, if I have a cut vertex, I just keep unfolding, unfolding, unfolding. Okay, and I can do that at most L times before my Whitehead graph will necessarily be disconnected. Okay, at which point, I'm say distance, at which point I'm distance 1 here from a free splitting, right? So call this at most L, right? And this is this free splitting where, my element G is elliptic. Okay, but now you can just do the same thing, right? If you have some T prime, you get some S prime, right? But this will also be a free splitting where G is elliptic. And so these ones will have distance 1. Okay. And so the diameter will be, like 2L plus 1. Okay. Okay. Simple enough. Okay. So what's the next case then? The next case is when your curve on sigma is not filling. Okay. Well, if it's not filling, it fills some subsurface. And I can look at one of the boundary components. Right? And well, that boundary component is simple, right? And the length of that boundary component is going to be bounded by the length of gamma on any hyperbolic metric. Right? So we have that, the length of alpha in any x is less than or equal to the length of gamma on any x, right? So that tells me really that, the region of Teichmuller space where gamma has length at most L is really contained inside of the region where alpha has length at most L. Okay. We showed this one's bounded, has bounded projection, so does that one. Okay, great. Simple enough. So, I mean, yeah, what's the case for free groups now? This is where things get interesting. This is really where a lot of the work lies. So that's when your element is, what's called Z simple. So it has a fixed point in some Z splitting. Oh, I should say something too. Yeah. So in this case here this was like all in the absolute case. In the relative case, it's essentially the same as well too. You just need to use a different version of Whitehead graph, which was due to Girardel and Horbet. And they also proved the same type of statement. So it's really just sort of plug in their work, and it's the exact same thing. Okay. All right. So we know that our element is Z simple, right? So we have some sort of, splitting of the free group over like a cyclic group. Okay. And that cyclic group has to be simple. Okay. It's a theorem of Schinitzer and Swarup that whenever you split a free group over Z, that element Z is going to be a simple element. Okay. And so you have something similar to this, right? I mean, I have my non-filling element, but I have this splitting of the surface group along the simple element, right? And I'm really using that simple element to try to control what's going on for the other one. It's a similar type of thing. I have like, my element G, right? Which, I can write in this, there's this free product with amalgamation of the free group over this cyclic element. And I want to say something like, I can find a Z splitting where like that element has some length which is bounded in terms of the original length. Okay, that's really sort of the main step here. So what I want to somehow bound length of an edge stabilizer in some, Z splitting where G is elliptic. Then I can kind of play a similar type of game. Okay, so, well, how do you understand splittings of this group relative to this element G? And so this uses this notion of what's called a decomposition space, which was originally defined by O'Toole. So what I want to do is I want to look at like the boundary of my free group, and let me just write it as a boundary of one of these trees. Right? One of the trees in outer space, the boundary is the same thing as the boundary of the group. Okay, and I just want to take the quotient where I look at all of the axes of G and I just crush them. Okay, so I take like my axis of G, take like the positive end, identify it with the negative end, and I just do this over all translates. So I just crush the boundary by, taking all of the axes of my element G and identifying them to a point. Well, individually, each one to a point. Okay. And it turns out that this is actually like the boundary, the Bowditch boundary of F, when I think about it as a relatively hyperbolic group with respect to the subgroup G. So assume G is not a proper power here. So this is really just, the boundary of this relatively hyperbolic group. And so, now there's, this idea, that goes back to Bowditch, in the context of hyperbolic groups, of, trying to understand splittings of the group by looking at the boundary. Okay. And so, this idea in this context here of looking at the decomposition space and trying to find splittings of the free group for which the element G is elliptic by looking at the cut points in this boundary was really, studied by Chris Cashin and Natasha Makura. Okay, and so I'm not going to write down anything really precise here. This is really kind of more of a philosophical statement. But they say, when the decomposition space is connected, which turns out is really implied whenever the element G is not simple. Right, so we've already dealt with the simple case, so we can throw that one out. And when the decomposition space is not the circle, so it's going to be the circle exactly when G is, you can write the F as the fundamental group of a once punctured surface, and G is the boundary component. Okay, so this what's called a quadratic element, so G not quadratic. And the point is, in this case, you have a surface already, so you can deal with this separately. Okay, but in these cases here, then there's really this connection between cut pairs with some adjectives in the boundary and Z splittings of F relative to the G. So there's this connection here between Z splittings of F rel G and cut pairs, like I said, with some adjectives here in the decomposition space. And so really, using this way of trying to think about splittings here, rel G, and looking at cut pairs on the decomposition space, they really prove a statement like this, where you get some sort of length bound on an edge stabilizer in terms of the element. And really, the tool there that they use is this notion of a Whitehead graph, which is related to the one I gave earlier. But when I gave the definition first, I was just thinking about removing a vertex and then looking at this graph, right? Well, you can remove like a larger subset of the tree, okay? And now you can play the same game, right? So you have this like subset of your tree, you toss it out, you have these components, and you can glue them up if you have some axis that connects them, okay? And really, they prove that by doing this construction, you can really model this decomposition space. Right, this decomposition space is kind of a hard space to understand, but they really build this up in terms of these graphs, that have like, you can essentially understand it with just finite amount of data. Okay, so that's really one of the key tools here, and they prove this proposition that. Well, do I have like 5 more minutes or something? All right. Well, let me just not write down anything else here more for you, so I can talk about the third case. So just say, Dash and Recurra really get us this thing that we want, okay? And now you can really kind of play a similar game to what we did before. You have this element here, this edge stabilizer that has this bounded length. Now you can kind of play around with the definition there to see that like this is also going to help you get a bound for the size of the projection. Okay, and so in the relative case here, like I said, this is really where like a lot of the work does in this in our result. So rather than just thinking about, the F as a relatively hyperbolic group with respect to this, I want to think about that free product as a relatively hyperbolic group with those free factors, and I throw on this additional element, okay? And so in order to like get this connection here between like splittings of that thing, rel all the data with these cut pairs and this corresponding Bowditch boundary, we really have to use a lot of the work of Chris and Dasgupta to try to understand what that boundary looks like and try to get these connections here, and work of Hallmark as well too for understanding how these splittings here are related to this boundary. Okay, but again, we come up with some sort of notion of like a Whitehead graph that allows us to sort of try to understand what this boundary looks like with some finite data, right? Because we need some sort of finite data so we can get some explicit bounds. Okay, so anyway, now just in the last 2 minutes or something, let me just say the last case here. So if it's filling, well, I mean, in this case, you can in fact see that like the Teichmuller space is bounded, right? Your curve goes everywhere on the surface. You really can't do too much without increasing its length, right? So this thing is bounded. The systole map is Lipschitz, okay? And so that tells you that, this one set is bounded, right? If I look at the systoles corresponding to Teich sub L of gamma, right, it's bounded. Right, but you want to get some sort of uniform bound, right? That's what we needed. Well, the point is that up to the action of the mapping class group, there's only finitely many curves that I can make have length less than L. So really, this is just a finite thing. Once I can show that it's bounded, I really get a uniform bound. Okay. Okay, so now for free groups, it's a similar type of thing here. Well, I don't want to say filling because we do it a little bit differently. Really, we do some sort of general, we end up sort of morally proving the same type of thing, that like if it's filling, meaning it's not Z simple, somehow the region of the outer space is bounded or so forth. But this is kind of where things get a little different, because in the relative case, we don't have this fact that up to the action of the group, there's only finitely many things whose length is bounded. And so this is actually one of the reasons we had to go through all of this stuff in the first place, was that like sort of at this last step here where you try to just prove something's bounded and then you say there's only finitely many things kind of fail. Because if you have this relative stuff, you're allowed to sort of do whatever you want to in the peripheral groups without changing the combinatorial length. And so we had to argue a little bit harder here in this last case to see that the thing is bounded. Yeah, I mean, essentially you do a proof by contradiction. You assume that you have, some sequence of elements that's not working for you. You take some limits and inside of outer space, I'll just write down some things here. You apply the Rips machine. And you end up then producing like an element that's like Z simple with an unbounded thing, and you get a contradiction. Okay, thank you.
That would come from your theorem. You have the right setting that you layering in periodic direction. Want some layering.
Yeah. No, like I said, you need now to like go back and like kind of, in general, you sort of, like take your elements and you kind of want to break it up into these chunks. And you just need to know that like these chunks actually kind of grow. And this statement says that if you have some sort of, collection of chunks of size at most L, those things will grow at some point. And so now you need to kind of put this into like, a machine here saying, if these kind of chunks grow, you kind of count how things kind of interact. And you'll see that you get some sort of uniform growing. So you really just, we didn't really need this for all L. We really just needed this for some L, but I don't know what that L is. I don't know if that answered your question. Okay.
Is the Z vector graph hyperbolic?
Yeah. Mm-hmm. Yeah, so it's in the absolute case, it's the same thing as the cosurface graph that Spencer and Sam defined. It's the same thing as like the main component of the intersection graph that was defined by Kapovich and Lustig. So there's sort of various models of these things. This one's kind of nice because it's kind of, like you can sort of think about a lot of these out of n complexes in sort of the same, really with the same set of vertices, and you're just kind of adding edges in a different way.